Properties of fractals. So first, let's talk about what is a fractal. Well, a fractal is a never-ending pattern that repeats itself at different scales. So when we talk about different scales, we're talking about some are small, some are big, right? But it's a never-ending pattern. And the pattern could be very simple, but when you consider that pattern that continues to repeat, the image that it produced can be very, very complex. So let's talk about the properties. Property 1, self-similarity. The shape looks roughly the same at different scales. So whether we're looking at just one piece or the third piece, whatever, that looks basically the same. So this is called the Sierpinski triangle, and these are the first 4 stages. So if you think about the very first upper left hand as just a straight solid black triangle, and then the next one, you can see it looks like we just cut a white triangle out of the middle. And then the next one, we do the same, right? So you're just constantly breaking it apart. And so you can see like every time this image is just continuing to be broken down. So it looks the same, no matter which one you're looking at, just some are bigger and some are smaller, right? Then property 2, iteration and recursion. So this means we start with a simple shape, which is the initiator, and we continue to add scaled copies of a generator, which means it's some kind of change in the shape. So maybe it's a bump, or maybe it's a curve or a twirl or whatever, but we have that generator and we add scales copy. So for each stage, when we talk about stage, it's like we start with something, and then stage 1 is we add that generator. And then stage 2, we add another generator, right? We continue to just repeat, because remember, we're repeating the same thing. That's the idea of fractals. So for each stage, replace every copy of the scaled initiator with a scaled copy of the generator, rotating as needed. For example, we have this piece. So you can see in 1, we start with a segment SE. The generator, then we curve it, right? Now we have a right angle. So now you can see we're going to take that curve and then we're going to just move it around. So you can see this is just right angles being added and moved. So while this was a very easy shape to start with, look at stage 9. Now it's become quite complex because we continue to add a smaller scale or a different scale of the generator. So these are fractals. Property 3, scaling. So the length of each part of the fractal, as well as the total length of the fractal will depend on the stage, right? So the beginning, we're going to have a different size or the length as we do at the end. So generally, as stages progress, the length of the sides get smaller while the total length gets larger, which makes sense. If we go back to this, look at stage 1. We have a long piece. Stage 9, the particular pieces are smaller, but the entire thing is longer. So that's what we're talking about there. Property 4, fractal dimension. The dimension of a fractal is based on the relationship between the initiator and the generator. So from initiator to generator, what is the scale, or how is it scaled? How much was it scaled down? And that gives you the value of S. To generate the next stage, how many copies of the generator do you need to use? Right? So to get the next stage, do you have to use 4 or 5? That's something. And that gives you the letter C. So this formula can be pretty tricky. So C equals S to the D. Okay, so for an example, if S is 4, mean that we scaled down by a factor of 4, and C is 6, meaning we needed 6 copiers of the generator to create the next stage, the dimension can be found by 6 equals 4 to the D. Well, to solve for D, we're going to use logarithms. So we log both sides. That'll give us D equals log of 6 base 4. We use the change of base formula, log of 6 over log of 4. And so we get the dimension of 1.29. So that's probably the least important piece of this, but just to understand the different properties of what makes a fractal a fractal.